Software is a very important component of the computer system. Hardware is nothing but a collection of circuits and electronics. Software is the one that actually enables the computer to do what it needs to do. A 1984 Time magazine cover captured a very young Bill Gates, but it also captured the essence of the importance of software with the title that said, "Computer Software, the Magic Inside the Machine." Everything that your computer does is controlled by this software. Now, there are two broad categories of software. There is application software and system software. Application software, you're used to it. You've done word processing, you've sent emails, you've definitely played games, and you've used web browsers. All these are examples of application software. These make the computer useful for everyday tasks, things that you do every day. Word processors, you have so many different kinds. You have Microsoft Word, you have Sun, Office, etc. System software, on the other hand, are programs that control and manage the basic operations of your computer. An example, when you first turn on your computer, you probably see Microsoft Windows coming up. That is system software. If you're using a Mac, you probably see the Mac OS X. That is system software. If you're using a Linux, Linux is an example of system software. Operating system, it controls all of the operations of every single component of your computer. So you've seen when you've tried to print and your printer is out of paper, you get signaled. Who is responsible for that? It's the operating system that's responsible for that. Operating system is a piece of software. There are a group of programmers who wrote it. Utility programs such as virus protectors. And these are all examples of system software. Now, how do computers store data? We are so used to sitting at our keyboard and just typing in. For example, if you're typing an email, "Hey, how's lunch at 12 p.m.?" Now, the computer does not understand the HEY or the HOWS because those are all English. Humans understand English. Computers only understand zeros and ones. All data in the computer is stored in a sequence of zeros and ones. And that's a big part of your keyboard, is to translate whatever you type into zeros and ones. A byte is a small unit of measurement. Let's talk about the different units of measurement. A bit is the smallest unit of measurement in the computer. Actually, the smallest might be a nibble, but we're not going to talk about nibbles here. Let's talk about a bit. Electrical component that can hold it can hold a positive and negative charge, like an on-off switch. When you have a light, you can turn the switch off. You can turn the switch on. A byte is 8 bits. All data is stored in the form of bytes in your system. Computers use the binary numbering system, and the binary numbering system is a series of zeros and ones. And in your computer, your keyboard corresponds to what is called the ASCII storage scheme, which is the American Standard Code for Information Interchange. It defines codes for 128 characters, and your keyboard can produce most of those 128 characters. Nowadays, when you program web pages or in computers, there is also a Unicode coding scheme, which can also represent characters for other languages. Another storage scheme is the EBCDIC, that's EBCDIC, which is Extended Binary Coded Decimal Interchange Code, which defines code for 256 characters. EBCDIC is only used on IBM mini computers, mainframes, and IBM workstations. Most of your desktop computers and laptops use the ASCII or Unicode storage scheme. Here is an ASCII chart which I've retrieved from the archives at computerhistory.org. And if you look at this ASCII chart, you will see, for example, for the capital letter A, you have bit 100, and then you have, coming down to this side, 0001. Now, in binary 1000001, each bit has a place. The first bit, which is B1, is 2 raised to the power of 0. B2 is 2 raised to the power of 1. 2 raised to the power of 2, 2 raised to the power of 3, 2 raised to the power of 4, 5, and 6. 2 raised to the power of 0 is 1. 2 raised to the power of 1 is 2, but that bit is turned off. So that means this bit is a 0 at this point. The only two bits that are 1 are the first bit and the bit at 2 raised to the power of 6, which is 64 plus 1, which is a decimal 65. You'll see more of this a little bit later. How does a program actually work? We know programs are written in the current day. We write them in a very English-like language. How do programs work? Programs are written in many different ways. Programs, instructions are written in a high-level language, or in machine language, or in assembly language. Every CPU or every processor is designed to perform simple operations, such as addition, subtraction, etc. And the processor understands instructions that are written in machine language. The CPU does many things. It fetches data from RAM. It executes that data. It executes the program by using a fetch, decode, and execute cycle. In the fetch, the next instruction is fetched. In decode, the instruction is analyzed. The CPU determines which component of the computer system is going to carry out that instruction, and execute actually performs the operation. And here we have from your book a figure that shows the fetch, decode, and execute cycle. Now, assembly language, machine language, was a language of zeros and ones. Initially, all programs were written in machine language, which is zeros and ones. And of course, it was a gargantuan task to find out if something was wrong, something didn't work. Assembly language uses small mnemonics. For example, add AX, BX, which means add the results of registers AX and BX. Registers are very high-speed storage locations in the CPU. The assembler translates assembly language to machine language for execution by the CPU. So every assembly language program is run through the assembler. High-level language programs, the programmer doesn't need to know how to write assembly language instructions in high-level language programs. Assembly language is low-level, machine language is machine level. High-level language is far more intuitive to understand. For example, print hello. Very easy to understand. You're saying write out hello to the screen. Okay. Every high-level language has keywords. These are predefined words that are used to write the program in a high-level language. These are words that have a defined meaning in the language. You cannot change the meaning of these words. For example, print has a predefined meaning in Python. It means write it out to the screen. If has a predefined meaning. It's used in conditions. Else has a predefined meaning. It means, in English and layman's terms, it means otherwise. Operators perform operations on the data. We all are familiar with simple math operators such as plus, minus, multiply, divide. When we write programs, just like when we write English, there is a set of grammar rules to be followed. When I say in English, is this a rule? It's supposed to be followed by a question mark. If it's not followed by a question mark, it's incorrect. And there are certain ways in which we have to write things in English. If I have to find out, if I want to ask you the question, is this a rule? Well, then I have to ask it in that manner. If I ask, rule this is if, it's not correct. Similarly, in programming, there are very strict rules that must be followed when you write the program. Every high-level language instructions add some rules of their own, but at their base, most high-level languages are very similar. The simplest form of program is a statement, an individual statement, one statement that tells the computer to do something. Languages, high-level languages, can either be compiled or they can be interpreted. A compiler. With the compiler, you have to write the whole program. Once you've written the whole program, or individual self-contained parts of programs, well, then you run the program through a compiler. What the compiler does is it looks for errors of grammar. For example, if you're required to put a semicolon at the end of each line of code, have you put that? If you've missed out on that, then the compiler is going to get that error. Compilers, once the program is syntax error-free, which is grammar error-free, it translates the program into a machine language program, which then becomes a series of zeros and ones. Python is an interpreted language. It translates and executes instructions. So it translates the instructions as they are being executed. It interprets one instruction at a time. It does not produce a separate machine language program, unlike a compiled language. When you write source code are basically the statements that are written by you, and we'll get to that soon enough when we start writing your own programs very, very soon. Source code can produce several different types of errors. The first type of error is a syntax error, which prevents the code from being translated. Syntax errors are relatively easier to find. Most often your interpreter will flag that error. Syntax errors, for example, in Python might be if you didn't get your indentation right. Python indentation is very important in this language. The other types of errors are, going back to this slide, you can have runtime errors, which are errors that are generated when the program is running. Those errors are a little bit harder to find because they originate due to some error in the logic of the code. This is, excuse me, this is a graphic from your book. Print hello earthling is interpreted, is converted to machine language, it's sent to the CPU, and the CPU signals the monitor, and then it's written to the monitor. Okay, and at this point, I'm going to stop this video, and in the next video, I'm going to show you how to use Python.